Hi everyone. So sorry for the delay in videos. We'll try to be consistent, but because of PhD commitments, I am very slow. So let me, talk about the subspace topology today. Basically, like you do in vector spaces, you define what is a vector space, and for more examples, you look for the subsets of that vector space which is under the same addition and the same multiplication, scalar multiplication. They are vector space, and then you declare that as a subspace of that vector space. So something similar is here, but not only that, this subspace topology also provides you a class of continuous functions. So this can be, treated as um, what example of continuous functions, like particularly a class of. So let me begin with something, huh? So say you have, okay, so let X tau be a topological space and say capital A is a subset. That's all, subset. Okay, now if I define, for example, a map, say I suffix A from A to X by IA of X is X for every small x in capital A. So what is this? This is basically inclusion map. You may think, oh, it's inclusion map. Inclusion maps are continuous. But now you have to, think with respect to topological spaces. So A is just a set, right? A is just a set. I'm not giving any topology here, right? So the thing is, this IA need not be continuous for all topologies topologies on capital A. For example, this you guys can fill in the details. I will just give you like some examples. So for example, if I take capital A to be the interval minus 1 1 and say I take my X to be R, and let's say I take topology I need. So let's say real line only, meaning the usual topology. And along with A, let's take the topology on A to be, say, just phi and capital A. You can show that IA from minus 1 to 1 into X is not continuous. Of course, with respect to the above topology. So basically, you have to find an open set in real line R, which is not open in capital A. So I hope this exercise you guys can do. So I will continue. So the point is, not every topology will make this inclusion map continuous. So what should be the next natural question? The next natural question should be, okay, so what is our topology on A which makes this, inclusion map from A to X, the arbitrary setting, what I have written here, always continuous. Do you have an answer? I hope all of you might have an answer. So, what would be the answer to this question? So, the answer is yeah, just take A to be discrete space, meaning every set is open there. Discrete topology. So, definitely this map is gonna continuous. But is it of really interest? See, it's the biggest topology. It's not gonna give me anything, special. Right. Also, the topology on this A discrete has no relation with the topology on X. Right? We want to look when we call something is subspace of something, say in vector spaces or subgroup in groups, subring in rings. So there is a relation, right? Like from the given operations in these examples, your subspace should respect those operations, right? Or subgroup or subring. So something similar should be here also, right? So the natural question is, okay, this is a topology and it's the biggest. So what is the smallest topology, right? So what is the smallest topology on capital A, which is inside X, such that this inclusion map from A to X is continuous. So that's our goal, and we will establish this fact that what is the topology. So let us finally have our definition. So definition. mm, okay, yeah. So let X tau be a topological space and capital A is sitting inside X. Then subspace topology on A is by definition, it is the smallest topology on A such that this inclusion map from A to X is continuous. So this is a, very abstract definition. It's like in some sense categorical. We're not going into category as I have mentioned. Like initial lectures, what we will have will be very basic, and yeah, later on we will develop more and more and more geometrical ideas also. So this is very abstract, right? It doesn't gives me exactly, I mean, what is the topology, right? So let us have a theorem which will tell us what is this topology. So theorem, let X tau again same be a topological space and again A sitting inside X. Then tau suffix A, let us define like this. Hmm, okay, so you take an open set U in tau and you take intersection with A. So is the subspace topology. That is what our claim is. So see, now it's like groups, subgroups, vector spaces, subvector spaces. It's respecting the operation. So it's respecting the open sets of the ambient space X. So X is my ambient space. Ambient space means like the things which are kind of universal. Okay, so let us prove this. So what you have to show, guys, number one, tau is a topology on X. I think I can leave this as an exercise. We have shown various, things. Maybe something we can verify. Okay, let's verify the third property. So let say V alpha be a subcollection in tau A. Meaning, guys, V alpha will of the form U alpha intersection A or U alpha in where? The topology tau and alpha in this lambda for every. Right? What we want to show that its arbitrary union is also there. So what this implies, union of V alpha, alpha in capital lambda is nothing but union of U alpha intersection A. Now you can distribute intersection over union. I mean it's distributed, you can take it back. So what it would be? Union U alpha, alpha in this intersection with A. Where is this set, guys? This is in tau. Why? Tau is a topology. So are you done? Right? You are done. This is in tau. So like that, you can do the other property also. Okay, the next thing, what you have to show? You have to show that IA with respect to this topology, what we have defined above, is continuous. So this let me leave as exercise. Just you have to take an arbitrary open set, you have to look for the inverse image. That's all. Let us do the third thing. Are we done? No. We have to show this is the smallest topology such that this inclusion map is continuous, right? So let us take some other topology. So let tau A prime be any other topology on where A such that this map is also continuous. A tau A prime into x tau is continuous. Right? What you have to show, guys? So we will be doing, similar things in the coming lecture also. Coming or maybe after that, I don't know. So, yeah. So what I was telling you? Yeah. So what you have to show? To show tau is in fact contained in tau prime. Because that's what it will make the smallest topology such that this map is continuous. So let us take an open set. So let us take V belongs to tau A. You know the definition of V. What is the definition of V? V is U intersection A, sorry, where U belongs to tau, right? Now guys, so you may call this map IA prime, just to distinguish between those two maps. Although the definition is same. So if you write IA only, that also work. Just the topology is different. So that's why let's call it, okay, by a different symbol. Okay, so what we let us observe this thing. So U is in tau and I A prime is continuous. So what this implies is I A prime inverse of U, which is what? You can verify U intersection A is open in where tau A prime. What is U intersection A? It is what precisely V, right? So you get it. So what you will get? This V is open in, oh sorry, open in X comma tau. So open in X comma, oh so not X, sorry, A. So yeah, so basically what we can do like directly write belongs to tau A prime. So this implies this is open in A tau A prime. That is inside tau A prime. That's what you have to show. So tau A is contained in tau A prime, and we are done. So that's what. So I hope this is clear. So now we have precise definition of the topology. Which topology? Subspace topology. So it is in fact the smallest topology which makes the inclusion map continuous. Okay, I hope this is clear. So let me give you two exercises. Whatever is the spelling, sorry, forgive me for that. One, let B be a basis of X tau. Say A is contained in X. Show that B suffix A. Let us define it. Can you guess what it would be? I want to show is a basis of um, basis of subspace topology on A. Please fill in the details. Fill in and then prove it. It's analogous to what we have done above. This is a good hint, I guess. Second thing, also show that, let's say A is contained in X. These are topological spaces. Now, wherever we will take subset, we will take, if we are calling it subspace, everywhere we will take subspace topology only, no other topology. So, okay. So show that F sitting inside A is closed in subspace A. So A, if and only if. Can you guess? F is also of some form like this, say D intersection A, where D is closed in X. So try to show this fact. I may write some statement wrong, so you have to verify it if it is correct or not. So yeah, this is about the subspace topology, and there are like various things, various exercises regarding that, which we may also use sometime. So I will again refer you to look say Mankris or the standard book which I always follow for more and more exercises. Shinto topology. This is the Springer one. Or the Mankris, the standard book. No need to write any more details. Okay, so I think let me conclude this session by an example. Okay, by the way, one thing. So see, subspace topology just doesn't give you a topology on a subset, but it also gives you example of the continuous maps, more and more continuous maps, which are inclusion map. You cannot say array inclusion map, what is this is so obvious, it will be always continuous like we have seen. It might not be here. This is the example. Okay, so yeah. So let me, and this session by one or two examples. Examples. So let's say your X is real line R and your A is Q. So, so what about this set? Intersection Q. And let me define one more set. Intersection Q. So I want you to check these sets. Okay, I mean, it's very obvious. So, see, E is equal to G, right? Because root 2 and minus root 2, these are not rationals. And if you see this thing, this is open in R and this is closed in R. So you see this particular set, what we have defined, E or G, these are open, meaning closed and open, both. In where? In subspace A is equals to Q. So this is, one nice example. There can be many. So let's take one more. So let's draw some pictures. So let us say you have x is equals to R2 with the standard topology by Euclidean metric and A is your S1. Let me draw it pictorially and you have to verify the arguments. So let us draw A with some different color. Say red. So if you believe this theorem or result or property, whatever, where it is, yeah. So if you have a basis for the ambient space, you intersect it with the subspace, you will get the basis for subspace. Oh, sorry, I have said the answer to this. Yeah, you might have thought it before watching, and then you have moved on. So take some thing like this. Of course, the boundary is not included. So let me draw it differently. So yeah, so like this. So this is a basic open set in R2. So now, what will be the intersection, guys? The intersection will be just this open arc, right? So what we are getting from here, so basically these open arcs, okay, of course, of finite length, of finite length forms basis for the subspace S1. See, this visualization is very important. Similarly, I will urge you guys to try it for, say, R3 is equals to, say, S2, and then X equal to Rn, and A is equals to S, so it is N minus 1. So try to see what is this. If you observe, I will give you a hint. So if you observe, this is just homeomorphic to basic open set in R, right? It's just like an interval, stretch it out. So similarly, when you look on, say, sphere, so sphere will be something like this. In R3 now I am, okay? Let's have some, some intersection with some more. So what it is, when you intersect with it, it will be, the intersection would be what, guys? It will be like like something like this, excluding the boundary. So something like this. But the bound version of it. So you see, this is homeomorphic to basic open set in R2. So I want you to do this, and you can actually show the homeomorphism also, that we will do, maybe in some examples when we discuss homeomorphism. Okay, oh, I'm sorry. I haven't defined homeomorphism for you guys, right? So let me define homeomorphism. So what do you mean by homeomorphism? Let me write it separately. Homeomorphism. So f from x to y is an homeomorphism. So that is the equivalence which we talked in, the very first lecture, which we want in topological spaces. If number one, f is continuous. Number two, f inverse exists, and f inverse is also continuous. So this is what the equivalence is. So if you see line like this, open like this, just stretch it out. It will be homeomorphic to an open interval in R. So similarly, the bumped thing like this, just like a chapati, bumped, and you push the bump down, it will be like a open disk in R2. So this, why it will be homeomorphic, we will see that example. There is very wonderful example, but after doing something called product topology. So the aim of next lectures, number one, something called box topology, and number two, something called product topology. Then we will see, more and more examples of homeomorphisms and continuous map. So I hope this is sufficient for this session. Thank you very much. And yeah, I hope if you like the video, yeah, I know I'm going very slow, so because the intent of this lecture is to, target a large audience which doesn't have access to, say good teachers or say good material. So thank you very much, guys.